Hello, my name is Evan Ashley Shumway, and I will be showing you parts of a wave. There are two types of waves that I'm going to be covering in this video today. One is transverse, and the other is longitudinal. A transverse wave looks something like this and is usually represented in something like a water wave. There are many parts that go into a transverse wave. Here is the equilibrium, where everything is even and everything is zero. The parts of the wave that meet equilibrium are called nodes. And as there is many waves, there's going to be a bunch of nodes. There are also two other points, one at the highest and one at the lowest. At the highest are called crests. At the lowest are called troughs. There's also the lengths that are in between each wave, which are called wavelengths. The height that is from either the crest or the trough is called an amplitude, and the more energy a wave has, the higher the amplitude. With the idea of amplitude, there's also something called frequency. At the end of each wave, once it makes one full cycle, that would be 1 hertz. So there's about 3 hertz here. And if this is about, let's say, 1 second, that means we would have 3 hertz for every 1 second. Hertz being the measurement of frequency. Just like amplitude, frequency relies on how much energy a wave has. The lower the energy, the lower the frequency is going to be, along with the amplitude. The higher the energy, the higher the amplitude, along with higher the frequency. The other kind of wave is longitudinal, and like transverse waves, they also have wavelengths, which is the space between this more compressed area, which is called a compression, and this more spaced out area. This is a refraction where the wavelengths are much more together and smaller, and this is a rarefaction where the wavelengths are more spaced apart. And the full wavelength includes both the rarefaction and the compression. Once again, similar to transverse waves, a compression is equal to how much energy that a wave has. So the more dense a compression is together, the more energy a longitudinal wave has. Just how there are different types of waves, there are also different ways that waves interact with each other. If you were to talk directly to a wall, the sound of your voice would bounce back to you. Why is that? It is because of something called reflection, where when your wave, or usually, I'm using a sound wave for example, but when a wave hits something that's a solid medium, it doesn't have anywhere else to go but back from where it once came from. Another wave behavior is called the Doppler effect. And basically, this is where the another wave behavior is called the Doppler effect, which is a effect that as an object that is producing a wave is moving, it also changes the amplitude and the frequency. So this is how when something is moving towards you, you could hear it much more better than it would be if it was in front. Another wave behavior is called the Doppler effect, and this can be seen in objects that are producing waves but are also moving at the same time. For example, I drew this screaming, running man, and in the direction of which he is moving, the frequency and amplitude of the waves of his voice have much more energy and are in a higher frequency. But in the direction he's moving away from, they are more sparsed out. Um, and this can be seen with all kinds of things, like, for example, when a car is heading towards you and honking, it's going to be louder than it is than it would be in front of you. The last thing and the last behavior I'm going to talk about today is wave interference. And this is when two waves meet each other, usually in the same medium. In wave interference, there are two kinds. There's constructive, and then there is deconstructive. In wave interference, there are two types. There's constructive. In wave interference, there are two types. There's constructive and destructive. In constructive interferences, both of the waves are basically equal to each other. Their crests are the same, their troughs are the same. Basically, everything about them is the same. And when they interfere with each other, they end up creating one bigger wave that adds both of the frequencies and amplitudes together. So the energy is combined. In a destructive wave interference, both of the waves are basically the opposites of each other. And when they interfere with each other, they cancel each other out and become zero, or the equilibrium. Thank you for watching my Parts of a Wave project.